We've seen how to add vectors graphically, and now we're going to look at the mathematical way to do it. The mathematical way will always be a little bit more exact because it's being calculated as opposed to measured. However, either method will be acceptable, and they are both good to check the other one. So make sure you have your graphing calculator so that I can explain how to do this with the calculator, and let's get started. The first thing we want to look at is the properties of any vector. So given an x-axis and a y-axis, so x, y, and a vector drawn anywhere in any direction. So in this case, I drew this vector in the first quadrant, so it would be a certain angle, theta, north of east. And let's just call this vector A. What I want to do is break this apart into its component vectors. And all a component is the x value of the vector and the y value of the vector. In other words, it tells you how much of the x it goes into and how much of the y it goes into. And the way that you draw a component vector is by looking at the tip of your vector and seeing how far in the x, so in this case it's going to the right, and how far up in the y. So the tip of each component should line up with the tip of the actual vector. So that would be my x component, I'll call that ax, and this would be my y component, ay. So if A is going up and to the right, it needs a component that goes up and a component that goes to the right. And the angle theta right here is what relates the two. So this is how you would draw the x and the y components of the vector. And we're going to be doing a lot of components when it comes to forces coming up, but for right now, just know where the x and the y components come from. We don't have to worry about drawing them quite yet. So also recognize how the y component could also be drawn right here, but for simplicity we draw it going up the axis. So the length of this line right here is the same as AY. Redrawing this triangle, we have A's x component, and then A's, that's an x, y component, all related by the angle theta. So now we want to see what we know about AX and AY in terms of theta. It's a triangle. If we have A, which is the hypotenuse, and we have theta, we can easily find AX and AY using sine and cosine. So if I'm looking for AX is the adjacent side, and we have theta and the hypotenuse. The trig function relating adjacent and hypotenuse is cosine. So cosine of an angle equals the adjacent over the hypotenuse. Let me just label these on the triangle. So this is the hypotenuse. AX is the adjacent, and AY would be the opposite. So cosine of theta is equal to adjacent over hypotenuse, which means that cosine of theta would equal the x component over the actual vector. So in order to find the x component, AX would equal the vector times the cosine of the angle. So to find a vector's x component, you take that vector, you multiply it by the angle. If we want to look at now the y component, It's the opposite. Opposite and hypotenuse are related by sine. So sine theta equals opposite over hypotenuse, which means sine theta equals the y component over the vector. So the y component of the vector is equal to the vector times the sine of theta. This is going to pop up all year. Anytime you're looking for an x component, it's related by the cosine of the angle. Anytime you're looking for the y component, it's related by the sine of the angle, so long as your angle is relative to the x-axis. So as long as theta is relative to the x instead of the y, you can use sine for y, cosine for x. Before we start adding vectors, let's just look at sines. So in my coordinate system, that was not a straight line. Let's try this again. Y-axis, x-axis. Any vector in the first quadrant will have a positive x value and a positive y value. Any vector in the second quadrant will have a negative x value and a positive y value. Reason being, if you're going to the left, negative. If you're going up, positive. Anything in the third quadrant will have a negative x value and a negative y value, and anything in the fourth quadrant will have a positive x value and a positive y value. So what that means, your x components will only be positive if you're facing east. So anything going to the right will have positive x. Anything going to the left will have negative x. Anything going up will have a positive y. Anything going down will have a negative y. And these positives and negatives are going to have to be what you identify based on the direction that the vector is going. So north of east, north of west, south of west, and south of east. And if you have trouble remembering what it should be, just think in terms of the coordinate system, and that should help you figure it out. So now let's start adding vectors. Let's say that I am given, and I'm just going to do this in words. Vector A is 5 centimeters at 61 degrees south of west. Vector B is 3.2 centimeters at 39 degrees north of east. Vector C is 4.1 centimeters at 44 degrees north of west. And we want to do A plus B plus C. We could do this graphically and draw the resultant and measure it, or we're going to do it mathematically and get a much more accurate result. So the first thing you need to do is find the x and the y component for each of those three vectors. And the best way to do this is to make an xy chart. For A, and we're going to do plus B plus C equals. So vector A's x component, AX, will equal A times the cosine of theta. And I'm not going to write every single one of these out. So vector A, 5 centimeters, times the cosine of 61 degrees. Since we're dealing with degrees, make sure that your calculators are in degrees and not radians. To check that, just go to mode and make sure that the degree is highlighted. Then you're just going to hit 5 cosine 61. And this should be 2.42408, keeps on going. Because this is going to be too many numbers to ever store, let's just round to 2 decimals. So the x component for A would be 2.42408. 2.42. And if I put the units up here, I don't have to worry about putting them everywhere else. These are all in centimeters. The y component of AY, will equal 5 centimeters times the sine 61 degrees. So 5 sine 61 equals 4.37 rounded centimeters. Now we have to look at sines. South of west is in the third quadrant. So that means both my x and y values are negative. That's something that we have to put in. A calculator won't tell us. Let's now get the x and y components for b and c. So the x component of b would be 3.2 times the cosine of 39 degrees. This rounds to 2.49. And the y component of b, 3.2 sine 39 degrees, is 2.01. This is north of east in the first quadrant. Both of those numbers are positive. Looking at vector c, x component is 4.1 cosine 44 degrees. This is 2.95 centimeters. Y component 4.1 sine 44 degrees is 2.85 centimeters. This is north of west, so my y component is positive, my x component is negative. A plus b plus c. All you're doing now is adding each of those components to get your resultant. So negative 2.42 plus 2.49 plus negative 2.95 gives me negative 2.88 centimeters as my x total. Over in the y's, negative 4.37 plus 2.01 plus 2.85 is 0.49 centimeters for my y. So what I have is that the x component of my resultant is negative 2.88 centimeters, and the y component of my resultant is 0.49 centimeters. But what I really care about is my total resultant. So what is the hypotenuse of the triangle that would form with the x and the y components? So you want to draw a triangle. I have a negative x component, so that means that the x component points to the left. And I have a positive y component, which means that my y component goes up. And my actual resultant vector, tip to tail, drawing in the resultant, will be the hypotenuse of this triangle. If you have the adjacent and the opposite, what we need to find is the angle and the hypotenuse. So the first thing I would do is find the hypotenuse using Pythagorean theorem. A squared plus b squared equals c squared, where a is your opposite, b is your adjacent, c is your hypotenuse. Again, it doesn't matter what is a and what is b. So we'll do rx squared plus ry squared equals r squared. Negative 2.88 centimeters squared plus 0.49 centimeters squared equals r squared. What I usually like to do is store these x and y values in my calculator as x and y. So if you store in negative 2.88 as alpha x and 0.49 as alpha y, it just makes it a little bit easier. So we take x squared plus y squared. This gives us 8.5345 centimeters squared for r squared. And then take the square root of that number. 2.921 keeps on going centimeters would be my resultant. So r equals approximately, and we'll just do 2 decimals, 2.91 centimeters for the magnitude. The last thing we need to do is figure out theta, the direction of r. We know that it's pointing to the left and up, so the direction will be north of west. All now you have to do is find theta. If you store these numbers in your calculator as x and y, you have the opposite, you have the adjacent. The trig function you would want to use relating opposite and adjacent is tan. So tan theta equals opposite over adjacent. Looking for the angle theta equals the inverse tan opposite over adjacent. And I'm running out of room, so go to the next slide. The angle will equal the inverse tan of your y component over your x component. The reason I like to store the numbers in my calculator is it makes it really easy to just do inverse tan of whatever you stored as y and x. So in this case it would be 0.49 centimeters over negative 2.88 centimeters. So this equals, in my calculator, I'm hitting second tan alpha y divided by alpha x. And it's going to give you a negative number if you have a negative. So in this case, negative here, it's going to give you a negative number. Ignore that negative, it's just directional. So theta would equal 9.655, keeps on going, degrees. That negative just tells you that it's not in the first quadrant. So my total resultant, and again, we're just going to round everything to 2 decimal places, is approximately 2.92 centimeters at 9.66 degrees north of west. And if you were to do this graphically as a check, you should get somewhere in the ballpark of these two numbers for the magnitude and the direction. So mathematically, it might take a little bit longer. It's a lot more numbers to deal with, however, it is more accurate, but it's not wrong to do this graphically. I'm going to do another example with subtraction. If you feel like you don't need to listen, then you can stop watching. But if you want to see the subtraction example, then keep on watching. Okay, let's look at, let's say vector A is 6 meters per second at 27 degrees south of east. Vector B is 2.3 meters per second at 20 degrees north of west. Vector C is 7.1 meters per second at 52 degrees north of east. And we want to subtract A minus B minus C. So we'll start with our XY chart. Put the units up here so I don't have to put them with all the numbers. And first thing I want to do is find the X and Y components for my 3 vectors. And we're doing A minus B minus C. And this will give us our resultant. So vector A is 6 cosine 27 degrees for the X component, so 5.35 meters per second. It's south of east, so my x component is positive, my y component is negative. And for my y component, we get 6 sine 27 degrees. So this will be 2.72 meters per second. For B, x component would be 2.3 cosine 20 degrees, 2.16 meters per second. This is north of west, so my x component is negative. My y component is 2.3 meters per second times the sine of 20 degrees, so 0.79 meters per second. North of west, so north means that my y is positive. And vector C's x component is 7.1 cosine 52 degrees. This is 4.37 meters per second north of east, so both x and y are positive. My y component is 7.1 sine of 52 degrees. This is 5.59 meters per second. So for subtracting, all we're doing is now subtracting instead of adding. So for my x components, we take 5.35 minus a negative 2.16 minus 4.37, and we get 3.14 meters per second for the x component. In the y, negative 2.72 minus 0.79 minus 5.59. This gives me negative 9.1 meters per second. So for my resultant, drawing my triangle, I have a positive x component. This is 3.14 meters per second, and a negative y component. Let's draw this a little bit better. I wrote a little too big. So 3.14 meters per second, and my y was negative 9.1 meters per second. So my resultant has a positive x and a negative y, which means that it will be in the fourth quadrant, so it'll be south of east. To find the magnitude of the resultant, we do our x squared plus our y squared. So storing these values as y and x, storing negative 9.1 as y, storing 3.14 as x. We do x squared plus y squared. It's 92.6696 meters squared per second squared. Take the square root of that number. We get 9.63 meters per second at, and then we need to figure out what this angle theta is right here. Again, theta is always relative to your x-axis. So take the tangent of y over x, so second tan y divided by x. You're going to get about 70, this will round to 70.96 degrees south of east. So subtraction is very similar to addition. The only thing you have to be careful of is that if you're subtracting a negative, then you're adding, and that you're not forgetting to subtract both for the x and the y's. Also, again, be careful of your directions of your given vectors, that you're adding in negatives where they need to be if something is going either south or west. So this is mathematical addition of vectors. We're going to redo pretty much all of our graphical addition with the mathematical to see how well they agree, and then you'll have a choice as to which version you like better, and that's vector addition.